Brownouts in a building can stem from various underlying electrical issues. A systematic approach to troubleshooting is crucial. Firstly, it is recommended to inspect all electrical connections throughout the building's electrical system. This includes connections at transformers, switchgear, electrical panels, and even individual outlets. Loose connections can introduce resistance into the circuit, leading to voltage drops that manifest as brownouts. Pay close attention to ensuring all connections are tight and properly made. Secondly, carefully evaluate the load on each circuit within the building. Overloaded circuits draw excessive current, which can cause overheating and voltage sags, resulting in brownouts. Verify that the current draw on each circuit does not exceed its rated capacity. If overloads are found, redistribute loads or upgrade the circuit capacity accordingly. Thirdly, transformers play a vital role in maintaining the correct voltage levels. Over time, transformers can develop faults that reduce their voltage output. To check this, test the transformers under load to identify any deviations from their rated voltage. If a transformer is found to be faulty, it may need repair or replacement. Fourthly, defective or damaged wiring can also be a source of brownouts. Poorly installed or damaged wiring can create high resistance points and voltage drops. Conduct a thorough inspection of all wiring, including cables, conduits, and splice points. Look for signs of damage such as fraying, corrosion, or loose connections. Replace any damaged wiring to eliminate potential issues. Fifthly, the neutral conductor is essential for maintaining voltage balance in the electrical system. Problems with the neutral conductor, such as loose, broken, or undersized connections, can cause voltage imbalances and brownouts. Inspect the neutral connections at the panels, transformers, and service entrance. Ensure that the neutral conductor is properly sized and securely connected. Sixthly, ground faults can create a path for current to flow to the ground, leading to voltage imbalances and brownouts. Locate and repair any ground faults promptly. Ground faults can be identified using testing equipment designed for this purpose. Seventhly, intermittent faults can be challenging to diagnose, as they occur sporadically. These faults may be caused by loose connections or failing components. Monitor the electrical system and use a process of elimination to isolate the source of the intermittent fault. Eighthly, harmonics, which are voltage and current distortions, can also contribute to brownouts. Nonlinear loads, such as variable frequency drives and electronic ballasts, can generate harmonics that distort the voltage waveform. If harmonics are suspected, install harmonic filters or isolation transformers to mitigate their effects. Ninthly, transient voltage surges caused by lightning strikes or switching operations can cause temporary brownouts. Install surge protectors at the service entrance and sensitive equipment to mitigate the effects of voltage surges. Tenthly, if the brownout issues persist despite addressing the above factors, it's worth contacting the local utility company. There may be problems with their distribution network that are affecting the building. Utility companies can investigate their equipment and lines to identify any issues that may be causing brownouts. Checking voltage levels at different points in the system using a multimeter is an important step. Normal voltage levels need to be confirmed. A voltage drop across a specific component or section of wiring can indicate a problem. Additionally, reviewing the building's electrical drawings and documentation can provide insights into the system's design and layout. This information can be helpful in identifying potential issues. Examining the service entrance where the building receives power from the utility is also critical. Verify the condition of the service entrance equipment, including the main breaker, metering, and grounding connections. Any problems in this area can affect the entire building's electrical system. Power quality analyzers can be used to monitor the electrical system for voltage sags, surges, and harmonics. These analyzers can provide valuable data for troubleshooting brownouts. Infrared thermography can detect hotspots in electrical panels, connections, and equipment. Hotspots indicate areas of high resistance and potential problems. When inspecting connections, it is important to use proper torquing techniques. Loose connections can be a major cause of brownouts. Proper torquing ensures a secure and reliable connection. Grounding and bonding are essential for electrical safety and proper system operation. Verify that the grounding and bonding system is installed correctly and that all connections are tight. Faulty or undersized equipment can contribute to brownouts. Check the specifications and ratings of all electrical equipment to ensure they are adequate for the load. Undersized equipment can overheat and cause voltage drops. Load balancing across the electrical panels is important for maintaining a stable voltage. Ensure that the load is distributed evenly across all phases of the electrical system. Imbalanced loads can cause voltage fluctuations and brownouts. Electrical components can degrade over time, leading to problems. Regularly inspect and maintain electrical components, such as breakers, contactors, and relays to ensure they are in good working order. Variable frequency drives, or VFDs, can cause harmonic distortion in the electrical system. Consider installing harmonic filters or isolation transformers to mitigate the effects of VFD. Electronic ballasts in lighting systems can also generate harmonics. Use low harmonic ballast to reduce harmonic distortion in the electrical system. Uninterruptible power supplies, or UPSs, are designed to provide backup power during outages. However, UPS can also be affected by brownouts. Ensure that UPS are properly sized and maintained to prevent problems. Backup generators can provide power during extended outages. Regularly test and maintain backup generators to ensure they are ready to operate when needed. Lightning strikes can cause voltage surges that damage electrical equipment. Install lightning protection systems to protect the building from lightning strikes. Power factor correction can improve the efficiency of the electrical system and reduce voltage drops. Consider installing power factor correction capacitors to improve the power factor. Voltage regulators can help stabilize the voltage in the electrical system. Install voltage regulators to maintain a consistent voltage supply to sensitive equipment. Transient voltage surge suppressors, or TVSS, can protect electrical equipment from voltage surges. Install TVSS devices at the service entrance and sensitive equipment to mitigate the effects of voltage surges. Insulation testing can identify damaged or deteriorated insulation in wiring and equipment. Perform insulation testing regularly to identify potential problems. Ground resistance testing can verify the effectiveness of the grounding system. Perform ground resistance testing regularly to ensure that the grounding system is functioning properly. Earth resistance measurement is critical to ensure proper grounding of electrical systems. A low earth resistance value ensures that fault currents can flow safely to ground, minimizing the risk of electrical shock and equipment damage. The recommended earth resistance value typically varies depending on local electrical codes and standards, but it is generally desired to be 5 ohms or less. High earth resistance can impede the flow of fault currents, leading to elevated voltage levels and potential safety hazards. Soil composition, moisture content, and temperature can all affect earth resistance. Sandy or rocky soils tend to have higher resistance than clay soils. Moisture helps to improve conductivity, while freezing temperatures can increase resistance. Regular testing of earth resistance is recommended to ensure that the grounding system remains effective over time. Soil treatment with conductive materials can help to lower earth resistance. Copper ground rods are commonly used to establish a low resistance connection to the earth. Rods should be driven deep enough into the ground to reach areas with consistent moisture levels. Multiple ground rods can be connected in parallel to further reduce earth resistance. Proper bonding of metal equipment and structures to the grounding system is essential for safety. Bonding ensures that all metallic parts are at the same electrical potential, minimizing the risk of shock. The size of the bonding conductors should be adequate to carry fault currents safely. Visual inspections of grounding and bonding connections can help to identify potential problems. Loose or corroded connections can increase resistance and compromise the effectiveness of the grounding system. Periodic tightening and cleaning of connections can help to maintain a low resistance path to ground. Surge protection devices, or SPDs, are designed to protect electrical equipment from transient voltage surges. SPD diverts surge currents to ground, preventing them from damaging sensitive electronic components. SPD should be installed at the service entrance and at points of use to provide comprehensive surge protection. The clamping voltage of an SPD is the voltage level at which it begins to divert surge current. A lower clamping voltage provides better protection for sensitive equipment. SPD have a limited lifespan and need to be replaced periodically. The lifespan of an SPD depends on the frequency and magnitude of surge events. Monitoring the status indicators on SPD can help to identify when they need to be replaced. Harmonic filters are used to reduce harmonic distortion in electrical systems. Harmonics can cause overheating of equipment, increased energy losses, and interference with electronic devices. Passive harmonic filters use inductors and capacitors to block harmonic currents. Active harmonic filters use electronic components to cancel out harmonic currents. The type of harmonic filter used depends on the specific harmonic profile of the electrical system. Harmonic analysis can be performed to identify the dominant harmonic frequencies. The size and rating of the harmonic filter should be matched to the electrical load. Regular maintenance of harmonic filters is essential to ensure their continued effectiveness. Isolation transformers are used to isolate sensitive equipment from the electrical system. Isolation transformers provide a barrier to common mode noise and voltage transients. Isolation transformers can also be used to create separately derived systems. The K-factor of an isolation transformer indicates its ability to handle harmonic currents. A higher K-factor indicates a greater ability to handle harmonics. Regular inspection of isolation transformers can help to identify potential problems. Power quality meters are used to measure various parameters of the electrical system, including voltage, current, frequency, and harmonics. Power quality meters can be used to identify power quality problems such as voltage sags, surges, and harmonics. The data from power quality meters can be used to troubleshoot electrical problems and optimize system performance. Power quality meters can be connected to a network for remote monitoring. Regular monitoring of power quality can help to prevent equipment failures and reduce energy costs. The National Electrical Code, or NEC, provides guidelines for the safe installation and maintenance of electrical systems. Compliance with the NEC is essential for ensuring electrical safety. The NEC is updated every 3 years to reflect changes in technology and best practices. Local electrical codes may also apply and should be consulted. Licensed electricians are qualified to install and maintain electrical systems in accordance with the NEC and local codes. Regular electrical inspections can help to identify potential problems and ensure compliance with safety codes. Electrical safety training is essential for workers who work with or near electrical equipment. Training should cover topics such as lockout/tagout procedures, arc flash safety, and electrical hazards. Personal protective equipment, or PPE, should be used when working with electrical equipment. PPE includes items such as gloves, safety glasses, and arc-rated clothing. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. Following proper lockout/tagout procedures is essential for preventing electrical accidents. Arc flash is a dangerous phenomenon that can occur when electrical equipment is energized. Arc flash can cause severe burns, injuries, and even death. Arc flash studies can be performed to assess the risk of arc flash and determine the appropriate PPE requirements. Regular maintenance of electrical equipment can help to prevent arc flash incidents. Grounding electrode conductors, or GECs, connect the grounding system to the earth. The size of the GEC is determined by the size of the service entrance conductors. GEC should be protected from physical damage. Ground clamps are used to connect GEC to ground rods or other grounding electrodes. Ground clamps should be made of corrosion-resistant materials. Bonding jumpers are used to connect metal enclosures and equipment to the grounding system. Bonding jumpers should be sized according to the NEC. Equipment grounding conductors, or EGs, provide a low impedance path for fault currents to return to the source. EGC should be run with the circuit conductors. Conduit is used to protect electrical wiring from physical damage. Conduit should be properly supported and secured. Junction boxes are used to enclose wire splices and connections. Junction boxes should be accessible and properly grounded. Panel boards are used to distribute electrical power to branch circuits. Panel boards should be properly labeled and maintained. Circuit breakers are used to protect circuits from overcurrents. Circuit breakers should be sized according to the load. Fuses are also used to protect circuits from overcurrents. Fuses should be properly sized and matched to the circuit breaker. Transformers are used to step up or step down voltage. Transformers should be properly sized and ventilated. Capacitors are used to improve power factor. Capacitors should be properly sized and protected. Motors are used to power various types of equipment. Motors should be properly sized and maintained. Lighting systems are used to provide illumination. Lighting systems should be energy efficient and well maintained. Control systems are used to automate and control electrical equipment. Control systems should be properly programmed and maintained. The electrical system should be inspected regularly for any signs of damage or deterioration. Any problems should be addressed promptly to prevent further damage or safety hazards. Regular maintenance of the electrical system can help to extend its lifespan and improve its reliability. A well-maintained electrical system is essential for the safe and efficient operation of any building. The electrical system's design must adhere to the National Electrical Code, ensuring that wiring, overcurrent protection, and grounding methods meet safety standards. Proper sizing of conductors is paramount to prevent overheating and voltage drops, ensuring efficient power delivery. Overcurrent protection devices, such as circuit breakers and fuses, must be correctly rated to safeguard against short circuits and overloads. Grounding and bonding are essential for establishing a low impedance path for fault currents, minimizing the risk of electric shock. Regular inspection should encompass the verification of proper wire connections, tight terminals, and the absence of any insulation damage. Thermographic scanning can be employed to detect hotspots, indicating potential loose connections or overloaded circuits. Load balancing across phases is crucial for preventing voltage imbalances and ensuring efficient utilization of the electrical system's capacity. Periodic testing of ground fault circuit interrupters, or GFCIs, and arc fault circuit interrupters, or RFCIs, is necessary to confirm their proper functionality in protecting against electrical hazards. Voltage monitoring should be conducted to identify any sags, swells, or transient voltage events that could potentially damage sensitive electronic equipment. Harmonic analysis can help to determine the presence and magnitude of harmonic currents, which can cause overheating and equipment malfunction. Surge protection devices should be installed at the service entrance and downstream distribution panels to mitigate the effects of voltage surges caused by lightning or switching events. Power quality studies can provide a comprehensive assessment of the electrical system's performance, identifying areas for improvement and optimization. Energy audits can help to identify energy waste and recommend energy-saving measures, such as upgrading to energy-efficient lighting or installing variable frequency drives. Proper labeling of electrical panels and circuits is essential for facilitating maintenance and troubleshooting activities. Maintaining up-to-date electrical drawings and documentation is crucial for providing a clearer understanding of the electrical system's layout and configuration. Ongoing training for electrical personnel is necessary to ensure they possess the knowledge and skills to safely and effectively operate and maintain the electrical system. A proactive approach to electrical system maintenance can significantly reduce the risk of brownouts, equipment failures, and electrical hazards. Regular cleaning of electrical equipment, such as panels and transformers, is important to prevent the buildup of dust and debris, which can cause overheating and reduce performance. Verify the integrity of the neutral to ground bond at the service entrance to ensure proper grounding and minimize the risk of voltage imbalances. Check for any signs of corrosion or oxidation on electrical connections, and clean or replace corroded components as needed. Evaluate the condition of the building's lightning protection system, including air terminals, down conductors and grounding electrodes to ensure it is providing adequate protection against lightning strikes. Consider installing a power conditioning system to filter out noise and voltage fluctuations, providing a clean and stable power supply for sensitive electronic equipment. Implement a regular schedule for testing and calibrating protective relays to ensure they are operating correctly and providing proper protection against faults. Verify that all electrical equipment is properly grounded and bonded in accordance with the National Electrical Code and local regulations. Check for any signs of water damage or moisture intrusion in electrical panels and equipment, and take corrective action to prevent further damage. Evaluate the capacity of the electrical system to ensure it can adequately handle the building's current and future load requirements. Consider upgrading the electrical system if it is undersized or outdated. Conduct a thorough review of the electrical system's single-line diagram to ensure it accurately reflects the current configuration and equipment ratings. Implement a computerized maintenance management system, or CMMS, to track maintenance activities, schedule preventative maintenance tasks, and manage equipment inventory. Establish a strong working relationship with a qualified electrical contractor to provide expert assistance with troubleshooting, repairs, and upgrades. Regularly review and update the electrical safety program to ensure it is current with industry best practices and regulatory requirements. Encourage employees to report any electrical hazards or concerns immediately. Implement a robust electrical safety culture that emphasizes prevention, training, and continuous improvement. By implementing these measures, you can improve the reliability and performance of the electrical system and minimize the risk of brownouts.